In standard physics, the fine structure constant, alpha, and the strong coupling constant, alpha S, are treated as independent, empirical parameters, numbers measured in a lab and inserted into equations to make the models work. Refractive cosmology defines the fundamental physical vacuum, the tau metric, as a dynamic, viscoelastic continuum. In this framework, the vacuum is not an empty void. It is a medium that yields like a fluid under low stress, but stiffens into an elastic solid as energy increases. Within this continuum, macroscopic expansion and localized quantum mechanics evaluate as the deterministic consequences of fluid dynamics operating within that medium. The forces of nature emerge as orthogonal mechanical responses, different ways the same singular medium reacts to strain. This table identifies the kinematic nomenclature required to evaluate the vacuum as a continuous fluid. Tau represents the global time of the continuous fluid metric, while the localized geometric refractive index, N of R, dictates the path of acoustic shear waves through the vacuum. By applying these variables to rheological equations, we can resolve the unified cosmological Deborah number. Equations 356, 358, and 360 provide the mathematical bridge that links the electromagnetic interaction directly to the strong nuclear force. Our objective is to derive these equations from geometric first principles, demonstrating that alpha and alpha S are inextricably linked. We begin by defining a fundamental particle as a localized topological boundary, a defect moving through the continuous tau fluid. The fine structure constant, alpha, measures the electromagnetic coupling. Mechanically, this evaluates as the dimensionless geometric probability of internal acoustic strain leaking outward from the particle boundary into the macroscopic vacuum. This geometric formula captures that probability, mapping a fractional wave vector as it leaks transversely out of the spherical boundary. In continuum mechanics, this rigid elastic response is the storage modulus, or G'. Electromagnetism is the outward expression of the vacuum's capacity to store this transverse elastic shear energy. Because this storage occurs transversely to the direction of flow, the electromagnetic force functions as the elastic component of the vacuum's total mechanical strain. While transverse strain leaks outward, there is a simultaneous inward longitudinal fluid compression occurring within the exact same boundary. This internal longitudinal fluid containment evaluates as the strong fluid coupling, alpha S. At the rest energy of an electron, this fluid fraction reaches a value of exactly 1. This state, where the vacuum acts as a yielding fluid, is the loss modulus, G'. It dictates total localized fluid confinement, or color confinement. The strong nuclear force is the viscous fluid response of the vacuum, preventing internal volumetric flow at low energy states. These two forces represent the division of energy at the particle boundary. One portion is stored elastically, while the other is dissipated through viscous fluid flow. We map this energy partition using the viscoelastic phase angle. The horizontal base of this right triangle represents the elastic response, the electromagnetic coupling, alpha. The vertical leg represents the viscous fluid response, the strong force, alpha S. The phase angle, delta, represents the distribution of energy between these two modes. Trigonometry defines their relationship. The loss tangent, or the tangent of the phase angle, is equal to the ratio of the strong force to the electromagnetic force. This proves that alpha and alpha S are not separate phenomena. They are orthogonal expressions of the same mechanical strain. The ratio of these forces is not static. It shifts as the interaction energy applied to the continuum increases. This dynamic scaling is governed by equation 356, the cosmological Deborah number, D. The Deborah number compares the frequency of kinematic agitation, the energy, to the intrinsic relaxation time of the metric. It determines if the vacuum will behave more like a fluid or more like a solid. Substituting this into our phase angle geometry results in a clean ratio. The strong force divided by the electromagnetic force equals 1 over the Deborah number. As the continuum is subjected to higher kinematic interaction rates, the mechanical rheological response of the vacuum shifts. We can now apply this dynamic scaling to high-energy quantum interactions to explain the phenomenon of asymptotic freedom. As interaction energy approaches infinity, the agitation frequency far exceeds the local fluid relaxation time. The Deborah number diverges, causing the phase angle to collapse towards zero and the vertical leg, the strong force, to shrink. This collapse triggers a phase transition. The vacuum flash freezes from a yielding fluid into a rigid Maxwell solid. While a solid supports transverse electromagnetic shear, it resists longitudinal volumetric flow. This causes the longitudinal admittance of the strong force to mathematically drop to zero, the physical origin of asymptotic freedom. The critical limit occurs at d equals 1, known as the primordial glass transition. At this point, the moduli are equal, and the vacuum reaches a mechanical yield point where it can no longer sustain the strain. The metric fractures, nucleating the stable boundaries of hadronic mass. The electromagnetic and strong interactions are unified as symmetric geometric projections of a single yielding continuum,